Hello guys, so today I'll be talking about how to use ImageJ to quantify your Western blot. Western blot is a kind of membrane you have after running your protein sample through an SDS page. I currently have my image in RGB format, which is maintaining the color of my secondary antibodies, which are red and green. But to analyze, I need to convert this blot into a more appropriate white and black format. So what I do right now is go to the image, go to on your ImageJ tab because of the way my system is. You go to image and you select on color and you split channels. Good. So each secondary antibody you use is exactly like one channel. But that's my background. I just deleted that. Then I have this channel and the other because I used two secondary antibodies. What I want to quantify is on only one channel, so I'll just get rid of the other one. But I still have this in like white bands. I want my protein to be in black bands because that's what I want to quantify. So I go again to edit and now I invert. So inverting takes my bands from white to black. But I also want to kind of crop out this image so I don't have a lot of background noise. So in my ImageJ options, I pick on that rectangle box and kind of zoom out to focus on where exactly I have my protein. So now good. So on the upper part I have my protein and the lower I have my loading control. So what I want to do now is actually to assign each lane. But before that, if you have a plot that has a lot of background noise, you can actually subtract the background. But this doesn't apply to my gel, but I'm just showing how to do that. You just subtract and you can preview before you apply. But I'm not doing that, I'm just showing, and I'll just exit that. So now let's go into the analysis proper. So what you want to do is actually assign each lane. ImageJ quantifies your gel vertically, so you have to assign your vertical lanes, right? So to do that, you actually need to like draw a rectangle over each. So you choose your rectangle from the ImageJ tab again and you draw. But one thing I like to do before I assign each lane is that I take that first drawn lane and kind of try to make sure that each of the other lanes that I have also fits that size. Because once I assign that lane, I have to maintain the same lane to quantify to make sure that there is equal quantification. I hope that makes sense. So I go through. If I see that what I drew out for my lane is too small for some of my bands, I kind of increase it. So now I've drawn a bigger lane and that works. So then once I see that works for everything, then I can go back to analyze, go to gels and select my first lane. Okay, so again now I can just click on that and drag it to my next lane. Now instead of saying select first lane, what I'm going to do is select next lane. So again, you go back to analyze, go to gels and select next lane. Awesome. So you're just going to do the same thing for all your lanes that you have. You can just click and drag and select next lane. You can also use the arrow key on your keyboard to move the cropped out lanes, but that kind of takes longer. If you want that, you can also do that. So now I've selected all my lanes. I have 7 lanes, and now after selecting the lanes, I actually plot the lanes. Awesome. So this is what we are interested in. So each band that you see there is represented with a peak in this graph. Each peak correlates with a band. So the software is very sensitive, even that there are some very faint bands that might not be so obvious to you, but software is able to detect that, and you know by the bands. For example, my first lane, it looks like there are only 2 obvious bands, but there is a very small inconspicuous band in between them, and there's also a peak for that if you look at my image there. So in total I have 7 graphs because I have 7 lanes, and in each graphs the number of peaks I have corresponds to the number of proteins, or like number of bands that I have in my image. So now I need to tell the software what is what, since now I have like some silent noise there. My lane, there is this straight line tool already selected for me to mark out what exactly is my protein and what is not. I'm going to take that tool and draw across. So the line between the horizontal axis and my peak is actually like background noise, and I need to eliminate that to tell the software what it should measure. So I take that straight line tool that I mentioned earlier and draw a straight line across one peak to the other to say, okay, this is peak 1. Right, this kind of subjective, but you just want to make sure you are doing it carefully, and you say peak 2. Good. Just make sure the lines touch both ends of the peak. So I do the same thing. Go on and on. Just kind of diligently go through all of this for each of your peaks. Yeah, same thing. You can see again, like I said, it might not look obvious to you, but there are some silent lines there, and the system is able to catch that, but you have to tell what it is. So now I've successfully selected. Now you take your magic wand tool, which I just selected, to quantify the area of each peak. So I kind of start with my loading control, which is the band under. So I select all the peaks for the loading control, right? Because I want the control on top. Then I select my actual sample, which is the one on top. I do that. The smaller bands are quite tricky, but you can also get them. Then you select. Good. So I know the first 7 readings are my loading control, but the area is just a percentage of the entire plot. So I go to label peaks because I will be using the percent, not really the area. So the first 7 readings is my control. I already prepared an Excel sheet, and I'm going to put that there. So the area and the percentage. Next, I will get the value for my actual samples, which is what I just put in there as well. So now we need to do some form of mathematical analysis. So my relative density, I need to find a standard. The way I already loaded my sample on the Western blot, I make sure like my standard or my control sample is the first sample. That kind of made it easier for me. So my relative density is like, I'll just do my standard percent over that same standard, but every other percentage will be divided by my standard. So C6 divided by C3, which is my standard. I just do that for every other sample. Just meticulously go through this and get all your data. It's divided by my control. Same thing for my loading control here. I have to divide the first loading control of my control sample with the percentage of that for every other sample that I have. Okay, so now that we have all of that done, but remember, I want to make sure that every expression of my protein is actually, I am looking at it relative to how the loading control is expressed. So I'm going to do an adjusted density, which is the relative density of that sample divided by the loading control in that same lane. I'm just going to do that real quick and drag down my cursor to just do the same command for every cell and just cross check to be sure I did the right thing. So now I can just put this data, which is the adjusted density, in a format that is easy for me to plot on graph here in Excel. And just put sample 1. Good. So now I can just insert a graph for this, and yeah, this just gives a rough sketch. For example, if each person knows what their sample is, but let's say I can see, oh, the protein of interest is reduced in sample 5, 6, and 7 compared to both the control and sample 2, 3, 4. I also put a PDF description of how to do this in my description box. So if you want to follow